prototyping and 3D printing. It's been around for a while, but we're going to go into a little bit about what it does and what it doesn't do. So 3D printing, I don't know if you've seen it a lot in the news, but there seems to be a lot of hype on it, a lot of talk about it. What is it? What is not? And Gartner put together this group of technology and their expectations, and you start with a technology trigger, and you go into the peak of inflated expectations, the disillusionment, and the slope of enlightenment as it gets to actually a full production. So right now, 3D printing is right there. So there's a lot of claims out there, there's a lot of discussions.
Computer? No, the computer.
Oh,
thank you.
There's a lot of discussions as to what it can do, what it can't do. You see things in the press every day claiming all these great claims. Now, one aspect of this is 3D printing, which is more of the desktop, has been around for a very short time, but additive manufacturing as a whole has been around since, for 20 plus years, SLA, SLS, etc. And so, as you look at this, you can see the differences, and what I'm going to be concentrating today is more on additive manufacturing rather than the actual small 3D printers. They have their place in society, and they will grow, but the additive manufacturing, which is more the commercial aspect, is what I'm going to be talking about today. So that's just the graph, the Gartner group, the different parts of it. This is 2012. So you've got the desktop here, and you've got the full-size commercial machine there. Big difference. And so what I'm going to go through today was product development, pre-production, and then production. Basically taking a prototype to concept and then hopefully to cash is what your goal is. These are some of the industries that utilize additive manufacturing. You can see the three biggest industries that our company focuses on is medical, medical equipment, business products, and aerospace. But we have all these other industries that utilize additive manufacturing. What's nice about this is that you have a lot of cross-pollination. So you'll have one industry like transportation having one idea of how to use a 3D printed part, and you can transfer that same concept into another industry that hasn't thought of it or hasn't utilized it. So there's a lot of cross-pollination and utilization of technology. So the additive manufacturing technologies that I'm going to go through today are polyjet, stereolithography, 3D printing or Z-Corp, selective laser sintering, fused deposition modeling, and direct metal laser sintering. This kind of gives a guideline of where you can see the additive manufacturing process fits in with other technologies. You have CNC here, and SLA, FDM, SLS. So you can see how it goes from a concept, and it covers prototype. SLAs stop pretty much at prototype, and then you go limited production and then full scale. So each of the different additive manufacturing have different capabilities, and they focus on, we're going to be talking about the pros and cons for each one so that you can get a good feel for that. Polyjet builds in 16 micron layers. It's essentially a print head similar to what you have in a standard printer, and it lays out both the material and also the support structure. So we're going to just...
Polyjet is a layer additive manufacturing technology used to develop plastic prototypes from 3D CAD data. This rapid prototyping process uses inkjet technology combined with UV curable materials to quickly and economically produce highly detailed and accurate physical prototypes. Polyjet is one of the fastest prototyping processes available to develop high-precision physical parts and is ideal for smaller parts, appearance models, and master patterns. The Polyjet process begins by slicing CAD data into cross-sections or layers as thin as 6/10,000ths of an inch. The data is then transferred to the Polyjet machine, which begins constructing the object one layer at a time. Similar to how an inkjet printer lays down pigment, the Polyjet printhead deposits small amounts of ultraviolet curable material on the build platform, eventually forming a single cross-section of the part. An ultraviolet light attached to the printhead simultaneously cures the material as it is printed. Once a cross-section is complete, the build platform is lowered slightly to make room for the next layer. As the part is built, support material is added to give supplemental strength to fine structures and down-facing surfaces. After all of the layers have been created, the finished part is removed from the platform and cleaned. Although finishing is not necessary, a number of hand sanding and paint options are available from service providers such as Solid Concepts. Polyjet parts are well suited for quick, economical prototypes requiring exceptional detail, surface finish, and edge visualization. Polyjet is ideal for a wide range of industries, including medical, entertainment, consumer products, automotive, and industrial design.
So PolyJet allows for models that are very, they're for smaller, they're for higher resolution models. You get very clean layer lines, so you can have a very nice printed model in a very short period of time. And also with the Connex machine, you can do you can do,
Overmolds.
no, it's actually, what's the name of it? Connex machines does dual durometer, sorry. It does dual durometer, so you can actually print, and you'll see the example up there. So one part is hard, and the other part is soft. So you can put two different durometers on each other and get a part out very quickly and efficiently. We also have Zoom RP, which you can upload your data and allows you to get the parts the next morning. It's got a countdown timer, and if you get it in before the countdown timer, you can actually have it in your hands the next morning. It's just for quick services rather than owning your own. SLA, again, we're going to go to another video.
Stereolithography is a rapid prototyping process used to create parts from 3D CAD data in a matter of hours. SLA is a highly accurate additive manufacturing process and may also be referred to as rapid prototyping or 3D printing. Models created with this technology are typically used as concept models, for form and fit studies, or as master patterns for molding techniques. The SLA process begins when CAD data is sliced into thin cross-sections or layers, typically about 0.006 of an inch thick. This data is then transferred to an SLA additive manufacturing system containing a vat of UV curable photopolymer. The machine begins to build the part one layer at a time. Each layer is constructed from an ultraviolet laser that is directed by X and Y scanning mirrors. As the laser traces the cross-section on the surface of the resin, the liquid material is hardened on contact. Once a layer is complete, the build platform is indexed down to make room for the next layer. A recoater blade moves across the surface, ensuring a thin coat of fresh liquid resin is evenly spread over the object. The laser continues to trace and form each layer atop the previous layer, building from the bottom up. The completed part is then carefully removed from the liquid and separated from the platform. A chemical bath removes excess resin, and the part is cured in an ultraviolet oven. Any support structures are removed at this time. With numerous hand sanding and professional paint options available through service providers such as Solid Concepts, stereolithography has become an excellent economic choice for rapid appearance models. A wide variety of industries have embraced SLA, including medical, automotive, entertainment, aerospace, and consumer products.
So stereolithography is, PolyJet is like a printer head, and it sprays down a liquid polymer that is photocurable. SLA is a bath that is tracing the part in each and every time, so it's building from the bottom up. And you can get very large parts. So you can do architectural models, different wind tunnel testings. There's a variety of different materials that we have that you can do this, but here's some examples of some of the ones that we've done. This is Real Robot, Wall-E, we've done Iron Man. We actually did our own kind of Iron Man where we did it with stereolithography, and we call it ID Light. And typically this model would be about 320 pounds. He actually weighs only 29.5 pounds. He's 6'2". So it's literally a honeycomb structure that's supported by itself. That gives you a very large part that's very complex and can be painted very nicely. But again, it's just additive manufacturing. You're taking a technology and you're extrapolating on it to come up with different uses for it. Another example, we have this one out in the foyer. Half of it's printed with SLA, the other half is with cast urethane. So the SLA half is sprayed with soft touch paint, whereas the other half is cast urethane, and it's got the whole cast urethane process. So again, by just combining different technologies. Quick cast, I'm going to skip through this, but essentially it's like lost wax. Lost wax is for making metal parts. We've done some large, as you can see, some very large parts. We've done turbines 8 foot across, things like that for cast. Z-Corp is a fun one because you can get a part printed in 390,000 colors. So it comes out of the printer head as in color. So when you print these, for example, this is one that's, I think I have an example up there. It actually comes out printed like this. So you're actually able to read the text on it. If you flipped it over, you could see where all the screw holes are. You could see that you could read the warning label on the back, everything about it. So it's very nice to have a part in your hand to show a potential investor, to show your clients that might be wanting to test something. You put something in their hand and you say, well, is that the right size for you? You know, if it's a medical device and they're dealing with muscular dystrophy or one of the diseases, you want to make sure that it fits that client that it's going for. If it's for a car, how do your end clients use it? So being able to get it in someone's hand and validate it before you go to the injection molding process or you get too far down the line, or come up with different ways of doing it. So it's just it's a fun way to get a product in your hand or in your potential customer's hands very quickly and test it out. Selective laser sintering is a process. We've gone for those SLA, Polyjet, and Z-Corp are all fit and form. In other words, they show a model, but they're not really durable. Okay, they're not durable parts that you can bounce, you can throw up against the wall. SLS is a completely different process. It uses a nylon 11 and nylon 12 for manufacturing. It uses a powder-based system for printing that powder.
Selective laser sintering, or SLS, is a rapid prototyping technology that turns 3D CAD data into physical parts in a matter of hours. SLS is an additive manufacturing technology that uses powered nylon 11, nylon 12, and PEEK materials. Parts produced are lightweight, highly durable, and both heat and chemical resistant, making SLS an excellent choice for producing production parts without the expense of tooling. The SLS process begins by splitting 3D CAD data into thin cross-sections or layers. The data is then transferred to the SLS additive manufacturing equipment. The machine then begins to create the first layer. After a leveling roller spreads a thin layer of powdered material across the powder bed, the CO2 laser traces the cross-section on the material. As the laser scans the surface, the material is heated and fused together. Once a single layer is complete, the powder bed is lowered to make room for the next layer. More material is introduced from the powder cartridge and rolled out smooth, while unused material is recycled. The process is repeated, building layer upon layer until the part is complete. As SLS parts are built, they are encompassed by unsintered powder, which provides supplemental strength and eliminates the need for support structures. Complex designs and assemblies, once thought impossible, are now being redesigned with SLS as cost-effective integrated structures. Solid Concepts manufactures parts utilizing nylon with property-enhancing fillers to create rugged SLS parts suitable for a variety of prototype and production applications. Typical uses for SLS include tools and fixtures, fuel tanks, flight-rated components for unmanned aerial vehicles, automotive designs, air ducts, architectural models, and artistic sculptures.
So SLS is basically a powder nylon, 11 or 12, and you're able to print it. So what's nice about it is that it prints, and it, unlike many of the other ones that require support structure, it has its own support structure as it's building. The powder is its support structure. So you can do very complex parts and shapes that are very durable. This is an SLS piece, that's strong and durable. You can throw it on the ground, it'll bounce back up. It's strong. They're used in aerospace, they're used in automotive. I'll show you some examples of that later. But essentially, you can stack the different parts in there. It basically 10 thousandths between them. You can fill the entire tub full of many parts. Last year we did 218,000 unique geometries prototypes. A majority of that was printed, because you can fill up a unit and completely. One of the other aspects of it is that you can take a conventional multiple piece assembly. So if this was on an airplane and you had 16 parts on it, there's a lot of points of failure. But if you build it in SLS, you can have it as one unit. There's no points of failure. And you can actually attach dog tags to it, so you have traceability all the way back to the material, when it was built, who built it, etc. So there's a lot of benefits to using SLS for rapid manufacturing and actually creating parts. Conformable gas tanks is something that the UAV industry has been using a lot. So when you want to take a unmanned aerial vehicle and you want to maximize the amount of gas in there, well, you can change the gas and you can push it into areas that would be impossible to mold or to cause it to go into. but if you're able to grow it from an SLS perspective, and it can cover wires, it can go around different branches, it can completely utilize the space to the maximum ability. So it's conformable in that sense. And then it can be coated, and it will hold liquids. I was talking with someone today, they were talking about a project that they did for Beckman Coulter, and it was actually for slides. And it was holding these slides for cleaning it. So it would actually hold the cleaning solution in the slide, and it was for production parts, you know, to produce a, to protect or produce, to clean the slides through the process. SLS can also be used, it's very functional, 350 degrees. This is used on Porsche for underhood applications. The dashboard on this racing team, we did all that dash parts of it, and rather than doing complex machining parts, you're able to grow the part in SLS and get it up and functioning in a matter of days rather than weeks. And you can change it. It's a digital file, so if you want a different file, you go print it. It's not something that you have to go back and then redo the machine. Yes, you have to change the CAD file, but you can have it up and running, and you can have it literally the following day. This is the application that was talked on video. They're having a hard time with this one as far as the welds and stuff. 4 of these fly in every Apache helicopter. It's made out of PEEK. We have one of the 2 or 3 printers that actually print PEEK with SLS in the United States. There's a gimbal printed as one piece. So you can do very complex shapes. This is an exoskeleton that you can actually, you're taking a SLS part, and you can do it also in cast urethane, and you can put an exoskeleton on it. So you have the strength of metal, but you have the weight of plastic, and you're basically marrying it, so you're trying to find the best of both worlds. Fused deposition model, it uses true thermoplastics, and we'll hear a little video on that too. You'll see this part out there. What's nice about this fused deposition modeling is that you can have very complex shapes. This is done on the same machine as this. This is hand finished. This one's coming straight off the machine. So you can see the difference. It's hard back there, but you can see the layer lines and the parts on it, whereas this one looks like it's injection molded part. Let me just get this up.
Fused deposition modeling, or FDM, is a layer additive manufacturing process that uses production-grade thermoplastic materials to produce both prototype and end-use parts. This technology is known to accurately produce feature details and has an excellent strength-to-weight ratio. FDM is ideal for concept models, functional prototypes, manufacturing aids, and low-volume end-use parts. The FDM process begins by slicing 3D CAD data into layers. The data is then transferred to a machine, which constructs the part layer by layer upon a build platform. Thin thread-like spools of thermoplastic and support material are used to create each cross-section of the part. Similar to a hot melt glue gun, uncoiled material is slowly extruded through dual heated nozzles. The extrusion nozzles precisely lay down both support and thermoplastic material upon the preceding layers. The extrusion nozzle continues to move in a horizontal XY plane while the build platform moves down, building the part layer by layer. The finished part is removed from the build platform and cleaned of its support material. Raw FDM parts have visible layer lines. However, service providers such as Solid Concepts offer multiple finishing options to create smooth, even surface parts including hand sanding, assembly, and cosmetic paint. Since FDM parts are constructed with production-grade thermoplastics, including ABS, polycarbonate, and Ultem, they are both functional and durable. FDM is utilized in a number of industries, including aerospace, automotive, industrial, commercial, and medical.
So basically what you can do is you can test out the product in the type of material that you're planning to do injection molding, which is very unique. That gives you some flexibility. Again, each of the different additive manufacturing processes have pros and cons to them. Why would you use one over the other? So So end-use parts, short-run production, jigs and fixtures, FDM is great for that because it prints extremely flat. If you want to mimic sheet metal, it's great for that because it will print large flat panels with no potato chipping at all. Concept models, functional prototypes. So you can get a lot of different varieties of different parts. But again, each has got its niche. This is a part that's used on aerospace. It's about 20 inches long. I think it was 15 to 25 parts before, and it's now down to 1. You even have the wire ties attached to it, so that you're not having to go in there and glue. Even those wire ties might be a penny a piece. Trying to maintain them, get them glued in the right place, etc. By building a part so it's self-sufficient, you're not having to no longer maintain that. With aerospace, you have to keep the tools around for 20, 25 years plus. If you have a digital print, you don't have that requirement. You basically keep the digital print around. Largest parts is 36 by 24 by 36 as a single build. They can also be segmented together. We've done very large pieces, basically almost the length of this podium up here on the speaker page. DMLS, direct metal laser sintering. So similar to the powder that you saw in SLS, we're actually using metal and we're sintering it. So these holes in this part right here are conformable. So they're conformable cooling channels. They circle round, down, and come back up. So trying to CNC that would be almost virtually impossible. So you can create very complex shapes. DMLS, in compared to billet or rod or the material, is between 3 and 11% stronger because of the way it builds. So it's got a little bit, it's got less flexural strength, but the way it's designed is the tensile strength is extremely strong. So we do 17.4, 15.5, cobalt chrome, titanium. And this is a unique one because you basically utilize 2 different additive manufacturing processes. You've got the DMLS in the center, and then you've got the SLS on the outside. So you've got the strength where you need it, and you've got a weight reduction on the outside. These are some pressure points, some pressure taps, stainless steel, again, small parts. The size is pretty much 5 by 5. We can extend beyond there, but that's a sweet spot for it. Cooling channels built right into injection molding part. That would be very hard to. DMLS for titanium and putting implants in the body. This is an area that's going to continue to grow. No one wants someone else's knee put into their body. You want something that's a size for your body. And that's an area that's going to continue to grow. If you need a hip replacement, if you need a knee replacement, if you need cosmetic surgery, you want something that's appropriate for your body. So this is an area that's going to continue to grow where they're scanning the person's body, they're figuring out what sizes, and they're printing it for that person. It's truly where additive manufacturing benefits the medical community. So how do you choose? You've got applications, you've got a conceptual model. We saw some conceptual models out here today. We see some functional models. How do you choose when to go with a conceptual or functional? The part size, the resolution, material accuracy, delivery. Like, there's a lot of aspects of it. You've got all these different additive manufacturing. So what? When do I choose? Which one do I choose? And how do I choose it? So we put together a chart. It's kind of hard to see. I don't know if you can see it from back there. But SLS, you've got SLS, FDM, Polyjet, and SLA. So this side of the chart is basically if it's 5 to 7 inches and smaller, it fits an SLS or Polyjet. Do you want a form and fit part, so that's it just basically doesn't look right, does it feel right in your hand? Then it's Polyjet or SLA. If you want a functional part, it's SLS or FDM. But it kind of gives you a matrix to work from. Are there exceptions? Absolutely. But it gives you a matrix to allow you to kind of plug and play what some of your technologies. We saw some smaller parts. I'm sure there's some bigger parts out there too. But you can kind of choose which one is best for it. And with our engineers, they'll help guide you through that aspect of choosing which one is right for you. Medical applications is where we do a lot of our work. Handheld, carts, devices, scientific instrumentation, anatomical models. The need in the medical industry is huge because it's a speed to market, getting a product in market, making sure it's valid. I've been working with a human factors group recently for the 510K process and making sure getting a part in hand. Can the person that's going to be using this medical device push the button? Do they have the strength? Is the button located in the right place? Are they using it in left-handed, right-handed? So it's just getting the parts in someone's hands, validating what you think is right to make sure it's right before you go too far down the road. This is a Panos car, and you can see the dashboard, the vents, steering wheel. These were all made with SLS, and then they were covered with leather. So you look at this car and you go, wow, that's incredible. It's finished. They must have spent a ton of money. Well, they did spend money, but it was literally printed parts that then were covered. So you can take the technology and utilize it in a variety of different ways to get your your conceptual model out to people so that they can be wowed by you and your opportunities that you're bringing. So all the additive manufacturing process can really kind of shake your brain up and make you think. There are some very specific areas that are growing. Transportation is one of them. Aerospace uses a lot of the additive manufacturing. As I mentioned, prosthetics and reconstructive surgery is an area that is necessary, and it's going to continue to grow. We're seeing more and more of the DMLS and things like that. Quick cast for patterns, finding the right part. This is more for a generic, but even creating the parts that are right fit. For example, right now, if you go into hip surgery, a lot of times what they'll do is they'll literally take out 3 packs. They'll take out, let's just make up a size 5, 6, 7. They'll try 5. No, that's too small. They'll try size 6. Well, that fits right, but let's try size 7. So they've opened up 3 packs to test and get one, and yet they're all functional parts. That's a huge waste of money. So if you can figure out a way of getting something exactly for the person that they need, you're minimizing the cost and you're reducing the cost. Copings and bridges, that's a big area. Motorsports, taking parts and creating entire, I'm forgetting the word here, but basically you're shelling out the insides so that you're reducing weight but still having the strength. This is a micro cooler, just an example of one that required no additional support structure. They designed it understanding the additive manufacturing process in order to circulate air. Here's a heat exchanger. Again, if you understand the processes and the abilities out there, and we have design guidelines up on our website, you can understand why you want to do it one way. Different additive manufacturing technology, you need to change your design or approach it from a different perspective. And if it's just an iteration, if you're planning on going to injection molding, you can still use the technology to help guide you through that and make sure it's correct. Osseointegration, basically making it so that the bones can grow around the parts and actually grab onto them. If they're smooth, the bones are going to have a hard time grabbing onto the structure itself. But if you create a lot of matrices in there, you can allow the bone to grab onto it and have strength and durability. This is just a liquid lattice. If you were to take that concept and you need to have a fully strength part, you would typically start with this and maybe take out some of the parts. But again, with liquid lattice and utilizing the technology, you can still have the strength and structure and still have those holes going through, but without all the weight. So again, it's just thinking it from a different perspective. Most people approach creating a product from the injection molding side. This is taking it from a different perspective. You've kind of got to twist your mind and look at it from a different perspective. There are no rules with printing. There are rules with printing, but they're different than injection molding rules. You can have undercuts, you can have complex overshapes, you can have a lot of different things that wouldn't be acceptable in injection molding or would be very challenging. You can actually build a part that way. So who are we? We're founded in 1991. We have 7 manufacturing facilities. We have 192,000 square feet of manufacturing space, 9 technologies, 350 employees, ISO 9001 and AS 9100. We're a $61 million company. These are some of our locations: Valencia, Poway, Tucson, Austin, Troy, Michigan, and Phoenix. So we've got a lot of redundancy, which is nice. I don't know if you guys remember when the power got knocked out about 8 months ago. Someone flipped a switch. In those kind of situations, what's nice is that we could actually transfer if it were a longer period of time to a different location because of redundancies. We have 77 additive manufacturing machines, which again, I'll have clients come up to me and say, I want one in FDM and one in SLS, so I can compare them. And then I'll order 10 and actually do my testing on that. But sometimes they don't know exactly what they're trying to achieve with the part, so they'll order one of 2 different materials, or they'll take 2 different SLS. I want one glass filled, and I want one aluminum filled. And by doing that, then they're able to find the one that they want, and then they can produce more of them for testing and validation. But by having so many different machines and also 50 different materials, you've got a lot of choices. And that, I found that to be very helpful to customers and really appreciative of it. Full finishing capabilities. We're ISO, like I said, ISO 9001 and AS 9100. We have Boeing, Raytheon. Some of these are all aerospace, but they're awards, as most people in the aerospace know. They're hard to get and even harder to maintain. So, thank you for your time. We'll be outside afterwards. If you have any questions, we'll walk through the process with you and talk to you about your different areas or any design thoughts or what you want to do or why one technology would be good for you versus